In this lesson we're going to look at the magnetic field produced by a solenoid. Now a solenoid is a wire that's been turned into a coil. So before we look at that, let's just remind ourselves what we learned about a single straight current carrying wire as in the last lesson. And you'll remember that if we have a current which is going down into the paper, right, so the direction of the magnetic field will be clockwise like that. So if we reverse the poles of the battery, the current is now flowing in the opposite direction. It's coming up out of the paper, so the direction of the magnetic field lines are going to go in an anti-clockwise direction. So remembering that now, let's have a look at the magnetic field produced by a single loop. Now to start with, I'm going to keep things simple. So we've got an electric current coming up this way, up out of the paper, and then going around back into the paper. And I'm representing the field lines produced by the current flowing out of the paper here and going into the paper here with different colours. Obviously they're not really coloured at all, but just to help you distinguish between the two. At the moment I'm just keeping things simple. I just want to think about the direction of the field lines. So the current's coming up out of the paper here on the left, so that's producing an anti-clockwise magnetic field. And on the right here the current's going into the paper, so that means the magnetic field lines are going in a clockwise direction. Alright, so let's just extend these magnetic field lines a bit and see what happens. First of all, that produced by the current going into the paper, so we're looking at the red field lines you'll notice here. Okay, they're all going again in a clockwise direction. Now the field lines produced by the current coming out of the paper, they're all going in an anti-clockwise direction. Now what I want you to notice here is that inside the loop, both the red field lines and the blue field lines produced by the different parts of the loop are all pointing in the same direction. So inside the loop, the magnetic field will intensify. Okay, so I'll just write B for magnetic field, get stronger inside the loop, because these field lines are all pointing in the same direction. But outside the loop, the opposite happens. The red field lines are all opposing the blue field lines on this side, and on this side the blue field lines are opposing the red field lines. So outside the loop, B, that's the symbol for the magnetic field, is going to be weaker, because the magnetic field lines from the different parts of the loop will oppose each other. So the consequence of this strengthening or weakening of the field, depending on whether you're inside the loop or outside the loop, alters the shape of the magnetic field line. So they're not actually, in this case, concentric circles, but they look more like this. So what we've got now are concentric ellipses, and inside the field is stronger, and we can show the direction of the field lines. And you can see, looking at the direction of these field lines, you can see that this single loop is acting like a permanent bar magnet with a north pole and a south pole, and the magnetic field is flowing away from the north and towards the south, as you'd expect with a bar magnet. Now what happens if we add another loop to this one? Well, what will happen is the magnetic field in the center will intensify more, and if we add another one it will intensify more, and so on and so on. So as we add more and more loops, what's going to happen is the field strength in the center of the loops is going to intensify, it's going to get stronger, and the field strength at the side of the loops is going to get weaker. So in fact what we're doing as we keep on adding loops is we're forming really what we call a coil or a solenoid. Let's have a look at that now. So I've got the current flowing into the solenoid at this end and out of the solenoid at this end, and there you can see the magnetic field patterns produced by this solenoid. So what you notice straight away is that inside the solenoid the field is very intense, so you've got a strong field, and also you notice that it's uniform. The field lines are parallel and with equal intensity, so inside the solenoid the field is both strong and uniform. And outside the solenoid, well, the field lines have exactly the same type of pattern as you'd expect from a bar magnet. Okay, so it's like a bar magnet with a north and a south pole. This is a little bit tricky now, so let's just go back to our single loop, and you'll notice here, looking into this loop now, you'll notice that the current is flowing in a clockwise direction. So we've got I, okay, coming up here and around here is flowing in a clockwise direction, so we'll put clockwise, and that produces the north pole up here and the south pole down here. So going back again to our solenoid, if we view the solenoid from this end here, looking at this end, so I'm looking at the current flowing in this direction here. My current is flowing actually here in a clockwise direction, as with the loop, so that's a clockwise direction, so it's flowing around this loop in a clockwise direction, so that produces a north pole at this end and a south pole at that end. So the solenoid acts like a bar magnet with north and south poles. And so if I switch the poles of the battery and change the direction of the current so that the current's flowing in to the coil from this direction, then I reverse the sense of flow of direction around the coil, and I will change the poles produced by the solenoid, so that if we change the current direction, this will then become the south pole and this will become the north pole. Okay, so the magnet that we produced using this solenoid is known as an electromagnet. So just to recap, I can affect the strength of this electromagnet in three ways. Okay, as we saw in the previous lesson, we can increase the intensity of the magnetic field by increasing the current that's flowing through the wire. That's to say, increasing the current that's flowing around this coil. And as we've just really implied in this lesson, you can also increase the magnetic field strength inside this solenoid by increasing the number of loops that are present in the solenoid. So if I use a very, very tightly wound coil to make my solenoid with lots of loops, then that's going to produce a much stronger magnetic field in the center of the solenoid. If I have a more loosely wound coil with fewer loops, that's going to produce a weaker magnetic field, a weaker electromagnet. Now, in the next lesson, we're going to look at how we can intensify the strength of this electromagnet, of this coil or solenoid, by including a magnetic material in the core of the solenoid. Okay, so we'll look at that in the next lesson.